So this is going to be our part 20 of our discussion on control system engineering, and this is part 3 of our discussion on root locus. So far we have gathered quite a few rules for constructing root locus for linear time invariant systems, continuous time linear time invariant systems, and today we are going to look at the last few ones, and then we would have a complete set of rules that we'll be able to use to construct the root locus for any given system, okay, with minimal calculation. Again, we already have discussed the purpose of root locus and everything, so I'm not going to go to the details of those anymore, but there are a few things we still need to discuss, and which we will discuss. Okay, again, as usual, if you have any queries during the class, feel free to ask. Otherwise, we are going to have a discussion later on. Okay, in any case, before I even start today's discussion, I would strongly suggest that you go through the Modern Control Engineering book by Katsuhiko Ogata, and you would see that there are plenty of example problems solved in that book, and that will help you grasp the idea a little bit better. Okay, unless you solve a few problems, you might not be unless you solve a few problems, you won't be able to make yourself familiar with this concept, right? So in order to be able to solve these problems with relative ease, you need to look at a few worked out examples first. Okay, so I would strongly suggest that after today's discussion, you go through Ogata's book, especially the chapter on root locus, and you would see that there are plenty of solved examples. Just go through those. I'm not asking you to solve examples by yourself. Okay, just go through the solved examples. Okay, and you would see that there are plenty of solved examples there, and then try to do those by yourself. Okay, and again, come up with transfer functions, and you shall get a set of problems, and I have curated certain examples, certain problems there, and try to solve those. And the first thing that should be there in your mind is that if you cannot solve a problem by hand, just use Python for solving the problem for you, and then figure out where everything went wrong. Okay, where then try to figure out what is that thing that you couldn't understand or something like that. Okay, because whenever you're asking Python or MATLAB or anything of that sort to plot a root locus, what it essentially does, it just changes the value of gain k and calculates the root and plots it. Essentially, that is how the computer programs do work, right? So none of these rules the computer programs that plot root locus, they use none of these rules. They just vary the gain k. So essentially they start the gain k with 0 and increase the gain k up to a certain point, and for all those values of gain k, they calculate the roots and they just plot the roots. That is how you get the root locus using a computer, right? But that doesn't use those programs would not use any of the rules that we are discussing. Okay, so these rules that we are studying, or rather we are figuring out as we are going, are simply there for us to construct root locus by hand with minimal calculation, right? Again, this is a remnants of 1940s and 50s technology. So it's quite old technology per se, but again, this is designed to give you a better grasp on the subject. Okay, in any case, so we are going to continue with the rule number 7 and rule number 8, and we are going to see that seemingly similar problems might have drastically different answers. Seemingly similar problems might have drastically different answers. So these are the kind of things we are going to encounter today. All right, so just to recap, since this is kind of a continuous discussion on root locus, just to recap, there are a few things we have already discussed about the root locus. Again, what is a root locus? We essentially take a transfer function, okay, and close the loop and vary the forward path gain k. Okay, and this feedback transfer function could be something. Okay, this feedback transfer function could be anything. Okay, it doesn't matter. We close the loop and take the characteristic polynomial and find out the roots. So essentially we are looking at the closed loop poles as we keep on varying the forward path gain k. Okay, and we try to figure out how the how the locations of the closed loop poles change as we increase the gain k, because we are not only interested about the stability of the system, we are also interested about how the system behaves overall, okay, as a closed loop system. Okay, so and for that we use something called the root locus. The root locus is essentially the locus of the roots or the closed loop poles as we vary the parameter gain k, right? So and as we went on, we discussed a few rules. We figured out that the root locus would start at the locations of the open loop poles when k is equal to 0 and end at the locations of the open loop zeros when gain k tends to infinity, or if there are not sufficient number of zeros, in that case some of the roots would, or some of the closed loop poles would follow along the asymptotes and go to infinity. Root locus is symmetric about the real axis because if you have a polynomial with real coefficients, that polynomial can only have real roots or complex conjugate root pairs. That is how root locus is symmetric about the real axis. And those parts only on the root locus are only those parts of the real axis can be on the root locus that satisfy the angle criteria. So we also figured that out. So we saw that if I am standing on a certain portion on the real line, that portion of the real line would be on the root locus if I look to my right and I see that there are odd number of poles and zeros to my right, odd number of open loop poles and zeros to my right. All right, so that was our rule number 2 that we figured out. In rule number 3, we figured out breakaway and break-in points. So essentially, we figured out how to find the conditions at which two or more roots would coincide. Okay, and subsequently find out the gain at which that happens. Okay, not only the location at which this kind of things would happen, and also the gains at which this kind of things would happen. So those points are called breakaway and break-in points, and we also discussed the distinction of breakaway and break-in points in our last discussion. Okay, and we figured those out as well. So that was our rule number 3. Then in rule number 4, we used Routh-Hurwitz criteria and forced, or rather tried to force difficulty 2 in Routh-Hurwitz. So we took the denominator as polynomial of the closed loop system, essentially the characteristic polynomial, and we constructed the Routh table. And there we tried to force a difficulty 2 situation so that it would give rise to at least 2 poles on the j omega axis, at least one single pole pair on the j omega axis. That would give us a marginally stable system, and in this scenario it would indicate that if I increase the gain, go beyond that particular gain value, we would encounter instability, things like that. So we figured out j omega axis crossing using the Routh table, and we also figured out the particular gain at which those kind of things happen. So that was our rule number 4. Then we used rule number 5 essentially. So again, I combined a few rules, so this should be really rule number 5 and 6, but I just said this is rule number 5, and that is how we are going to end up with 8 rules instead of 10 rules in total. Okay, so centroid and asymptotes. So essentially what happens is that if you have p number of poles and z number of zeros, open loop zeros and open loop poles in the system, in that case z number of poles would reach the locations of the open loop zeros as the gain k tends to infinity, but the rest, so p minus z number of poles of the closed loop system, would go along the asymptotes. And we figured out how to actually calculate those. Where the asymptotes originate is called the centroid. Asymptotes would only originate at the on the real axis, so we figured that out, and we also calculated the number of asymptotes and their particular angles. Okay, so we figured those out as well. And then in rule number 6, we figured out situations where we would have circles on the root locus, so we figured that out as well. All right, so we figured out conditions on which you'd have circles on, right? So we did that. So existence of circles on the root locus, so we essentially figured out that there could be situations where there would be circular regions in the root locus itself, right? So now we are going to look into 2 more things, okay, or rather really speaking just one more thing. Okay, so let's start with that today. Again, during the discussion, if you have any query, just feel free to ask. I'll be definitely answering your query. So this is going to be rule number 7 today. Okay, and this is going to be the angle of departure and angle of arrival. So angle of departure and angle of arrival. So I'm just combining all the rules. So we are going to eventually end up with 7 rules only. Angle of departure from complex poles, an angle of arrival at complex zeros. So we are going to look into these today. All right, so that is something we're going to discuss today. All right, so angle of departure from complex poles and angle of arrival at complex zeros. So before I even go into this, let me remind you how we calculated the angle criteria, how we figured out that the angle criteria is being satisfied at this point, the angle criteria is not being satisfied at this point. So in order to do that, let me go back to our rule number 2, where we figured out which portions of the real line is part of the root locus and which portions of the real line are not. How did we do that? We figured out that the condition, essentially the characteristic polynomial, is this 1 plus k gs hs, and if I make it a characteristic equation, so I would equate it to 0, and when I equate it to 0 I get this equation. But this is a complex equation. This complex equation essentially has two things that it would need to satisfy, right? So the magnitude of the left hand side needs to be equal to the magnitude of the right hand side, and also the angle of the left hand side needs to be equal to the angle of the right hand side. It is just very similar in nature to having two complex numbers equal, right? So if I have two complex numbers that are equal, then the real parts would match and the imaginary parts would match. Evidently, if we represent the complex numbers in polar coordinates, essentially as magnitude and angle, in that case two complex numbers are equal only if their magnitudes match and their angles also match. So that is how we wrote down the characteristic equation for our closed loop system, right? So we wanted to satisfy these two equations. So only those roots satisfying these two equations together would be part of the root locus. So, and we are calling this equation to be the magnitude criteria and this angle equation to be the phase criteria or the angle criteria, right? Something like that. And we figured out that if I am standing on the real axis, okay, any part on the real axis that satisfies the angle criteria would also satisfy the magnitude criteria for certain value of gain k, and as such any part on the real line that satisfies the angle criteria would actually give me a valid location of roots, right? So we'll be able to calculate a certain value of gain k for which that part of the real line is on the root locus, and we calculated that by just simply calculating the total angle here. So we took an arbitrary point here, for example. So these are the locations of the open loop poles at s equal to -1, s equal to -2, and s equal to -3, and we took arbitrary points on the real line and we checked whether it is able to satisfy the angle criteria or not, whether the total angle is actually whether this angle of GSHS is an odd multiple of pi. Okay, it could be a negative odd multiple, positive odd multiple, but it has to be an odd multiple of pi in order for it to satisfy the angle criteria. So we figured that out. And while discussing the angle of departure and angle of arrival, we would use the same idea here. We would see that if we can satisfy the angle criteria, we would be able to satisfy the magnitude criteria as well. Because look at these equations very carefully. Okay, these angles, okay, these are giving you certain angles, right? And on the right hand side, in order for this to be satisfied, this angle criteria to be satisfied, these angles need to sum up to some multiple of 180 degrees, right? 180 degrees. So you don't really have any choice. Try to understand what is the variable that you were actually changing. What was the parameter of the root locus? The parameter of the root locus is the gain k, right? But if you vary the gain k, you are not doing anything with the angle. Try to understand. Okay, the gain k does not affect the angle criteria in any shape or form, right? The gain k, which is the parameter of the root locus. What is the root locus? Essentially, you increase the forward path gain k and you trace out the locations of the closed loop roots. But try to understand that the gain k only affects the magnitude criteria. It does not affect the angle criteria. The angle criteria is entirely determined by the locations of the open loop poles and the open loop zeros, right? Because this is what this is. This does not have k within it, right? And even if we had k, it would not affect it because k is a positive real number. So this angle criteria in a sense is completely independent of the gain k. So that is how solving for root locus, at least how constructing root locus really works. We figure out conditions which satisfy the angle criteria, and if we satisfy the angle criteria, then we would always be able to figure out a value of gain k to satisfy the magnitude criteria. Do you understand my point? Right? K, this value of K is entirely in my hand, right? And this is a positive number. So whatever the positive number I want, I can always change the value of gain K here to get that positive number, right? Whatever the positive number this one is, mod GSHS, okay, I can always figure out a certain value of K for which this equation is satisfied, right? So this equation can always be satisfied, truly. But whether or not this equation can be satisfied, that depends on the locations of the open loop poles and open loop zeros, because this equation is independent of the gain, forward path gain K, right? So this is how things work really. In order to figure out whether something is on the root locus, we try to satisfy the angle criteria. We try to see whether the angle criteria is being satisfied or not. And if the angle criteria is not being satisfied, in that case, we cannot do anything about it. But the moment we see that, okay, under this condition, this point is satisfying the angle criteria, then we can rest assured that we'll be able to figure out a value of gain K for which this criteria is also satisfied. Yes, absolutely. Someone is saying yes. So someone has just restated what I was just discussing. So satisfying the angle criteria is not in our hand, right? We have to figure out whether the point we are looking for actually satisfies the angle criteria, right? The point on the S plane actually satisfies the angle criteria. But if it does, then we would always be able to find out the value of gain K for which it does satisfy the magnitude criteria. So we can try to understand, we can make this, we can satisfy this at our will. We can choose whatever value. Say for example, I want this to be, so for example, we have chosen a certain value of S. Okay, we have chosen a certain value of S for which this is maybe 100. Then I can always choose K to be equal to 0.01 to satisfy this equation. So this equation can always be satisfied by us. So we can always satisfy this equation by choosing a suitable value of gain K. But this equation is not in our hand. Try to understand. This equation entirely depends on what poles and zeros we have, what open loop poles and zeros we have in the transfer function itself. So only the parameter K is in our hand, and that parameter K, we can use that parameter K to satisfy the magnitude criteria at our will. Okay, but we cannot satisfy the angle criteria that way. Okay, the angle criteria needs to be satisfied, then only we can look for the value of K for which the magnitude criteria is also satisfied. So that is how root locus really works. All right, so while discussing angle of departure and angle of arrival, let's discuss how we measured angles once more, right? How we discussed how we measured angles. So let's start with this. Okay, rather let's take this example and let's bring this to a new page, right? So again, we did that mathematically earlier, or rather analytically I would say, and here we are going to do it graphically, okay, to give you a better understanding of our point of view here, right? Again, this is kind of a graphical technique again, okay? So people invented quite a few graphical techniques back then because again, we did not have computers. Very simple, right? So say the transfer function we have been looking for. So say this is my GSHS. So GSHS is 1 by S plus 1, S plus 2, S plus 3. Okay, so that's the loop transfer function, right? And here are the open loop poles. Here are the open loop poles. Sorry, one is at -1, one is at -2, one is at -3. So here are the open loop poles. I think you can see it, right? So this is the j omega axis, so imaginary part of the imaginary part of the S plane, and this is the sigma axis, so real line. So this is the real part, right? So now if you recall the way we calculated the angles, we essentially just a moment, let me just mark this. So this is S equal to -1, this is S equal to -2, this is S equal to -3. So the way we figured out the angle criteria for parts on the real line, we simply did take points on this, right? We did take points on this, and this arbitrary point that is between these two poles here would be a part of the root locus, right? If you can recall rule number 2, because if I am standing here and look to my right, I would see odd number of poles. But where did that rule come from? We also see that, we also saw that, we saw that we really saw that this point here is part of the root locus, because the total angle, or rather angle of, so at this point angle of GSHS at this point was actually minus 180 degree, or actually 180 degree, whatever you want to call it, right? We saw that this angle was 180 degrees at this point, okay? But we also saw that if I am standing here, okay, this angle would be equal to 360 degrees. So that will be even multiple of 180 degree, okay, right? And here the angle would be 540 degrees. We figured something like that out already, right? So we saw that. So again, we calculated everything by just putting the value of this point in the angle criteria here. We just calculated the angles like that, right? So we essentially said that the angle of GSHS, the angle of this complex number, would be the angle of this whole thing, but the angle of one is 0, and subtract angle of these. So that is how complex numbers really work. So this would be angle of s plus 1 minus, sorry, the whole thing has a minus angle of s plus 1 minus angle of s plus 2 minus angle of s plus 3, okay? And since if the point is between minus 1 and minus 2, then this is a negative quantity, okay? This s plus 1 is a negative quantity, so that angle, since this is a negative quantity, that angle is going to be 180 degrees. So I had minus 180 degrees, and this would be positive quantity, so that angle would be 0 degree. This will also be a positive quantity, so that angle would be a 0 degree. So that is how we would have 180 degree for this point, okay? But for this point, similarly, this would be a negative quantity, this would be a negative quantity. So I would have minus 180 degrees, minus 180 degrees in total, minus 0. So I would have 360 degrees as such. But there is a graphical way of thinking about it. Okay, there is a graphical way of thinking about it. So let me just redraw what I had just drawn, and let us figure out the graphical way of thinking about it. Okay, so let's take these poles. So here is one, here is another, and here is another. Okay, so what is the graphical way of thinking about? Say I am standing here, standing at this point. So question is, how much is the angle? How much is the total angle contribution? Okay, again, even if I don't mark it, so this is at minus 1, minus 3, 0. That's the sigma axis, that's the geometry axis. Okay, all right. So now what is the total angle contribution? Now this can be calculated very easily, right? This can be calculated very easily, and the way you do calculate the angle contribution is very simple. You take a line, you draw a line from the poles towards this. You draw a line from the poles towards this. Okay, so let me give you an example. Say for example, if the point is here, so for example, if the point is here, so instead of saying this, let's just say hold on, instead of this, let us just say, so we are dealing with a point that is here. We are trying to figure out the angle criteria. Okay, we are trying to see how much is the angle, right? At this point, what is the value of angle GSHS? What is the value of that? So we would have to put this value of the point here, right? In this equation, we would have to put that value of S in this equation and figure out the complex angles, right? So that would be something plus j omega, and we have a particular value. So for example, if this is say minus 1.5 plus j2, would have to put that and sum this up, and then we have to take a tan inverse and everything, right? So we would calculate the angles. But what does that represent really? That represents this thing. Try to see. So for this first point, that would represent essentially this angle. So if we take a line and draw it from here, okay, that would simply represent, so this first part. So if we take the value of this point and put this here, if we take this value of this point and put it here, so that will give me a complex number, and complex number in the form of a plus jb, right? And what is the angle? Tan inverse a plus jb, right? So tan inverse b by a, tan inverse b by a. So if you calculate that, whatever angle I get would essentially be this angle, would essentially be this angle, right? Let's call this theta 1. Let's call this theta 1. In a very similar fashion, okay, if I put this point here, the value of this point, again on this equation, on this part, Okay, so if I take the value of this point and put this on this part, what I'm going to essentially get the angle as this one. And again, this would be very clear with the special example, right? So, and the angle would be simply this one, and let's call this theta 2, right? Again, we always measure the angle along the x-axis, right? We measure the angle along the x-axis always, right? And for the last one also, a very similar thing would happen. What am I doing? For the last one also, a very similar thing would happen, and as such, this is going to be the angle. That's going to be theta 3. Okay, and so we would know that these are the angles here, but we know that since these are the poles, the angles should have a negative sign, because whatever the angle I get out of this, a negative sign is appended therein. So essentially here for this particular point here, the angle of GSHS, since all of the angles are coming from poles like that, the angle of GSHS would be minus theta 1 minus theta 2 minus theta 3. Okay, so essentially we put the points here, so that way we could do it analytically, or we could also do it graphically, right? So again, since these are the angles like this, so we would essentially have minus signs like that, and at this point, at this very point here, the total angle like this would be minus theta 1 minus theta 2 minus theta 3. And again, how are we measuring the angle? We are simply measuring the angle like this. Hold on for a second. How are we measuring the angle? We are measuring the angle with respect to the positive direction of the x-axis, right? So whatever that angle is, so again, the total angle contribution is this one. Okay, so again, we always measure angle like that. So that's the angle contribution at this point, total angle contribution. So try to understand that this is a very simple thing to figure out, right? I don't think there is any complication here. Now, why am I calculating this? Because this point here, let's call this point S1. Let's call this point S1. Okay, this very point, let's call this S1. But the point is, this point S1 can be a part of the root locus, or rather would be a part of the root locus, if and only if, so that's a mathematical notation. Okay, someone is saying the network is not working, but it seems to be working here at least. You might have some network issue. Let me just refresh the stream. Okay, so root locus, if and only if this angle, okay, this angle, so this is essentially here minus theta 1 minus theta 2 minus theta 3 is an odd multiple of (180°). Could be a negative odd multiple, positive odd multiple, or any sort of odd multiple of 180°. Only then it would be a valid point here, right? Now think about the original case here. Think about this pretty simple case here, okay, where I had a point lying here. Okay, so this was the part of the root locus. But how can we assure that? We just take the points here. So for example, what is the angle contribution here in this direction? In this direction, what is the angle contribution? Let's draw this line like that. And here, what is the angle? That's 180°. Again, now from this, I'm drawing this. Now what is the angle? Of course, it's 0°, right? And again, from this, I'm drawing this. Again, what is the angle? 0°. So we have 0°, 0°, and this, right? So if you just think about it, if you you have to kind of use your imagination a little bit right now. If you take this point and bring it down here, you'll see that this angle becomes, if you take this point and bring it down here, you would see that this point, this angle becomes 180°. but this angle becomes 0 degree, this angle becomes 0 degree. So the total angle becomes minus 180 degree because of this minus sign. So it's an odd multiple of 180 degree. So that part would be on the root locus. But if I take this point and bring it here, if I take this point and bring it here gradually, this angle becomes 180 degree, this also becomes 180 degree, and this becomes 0 degree. So that way I would have entirety of 360 degree angle contribution, negative 360 degree here. So that way the total angle contribution is going to be an even multiple of 180 degrees. So that part is not going to be on the root locus. So I think that understanding is clear, right? So with that said, we use this idea to figure out something called the angle of arrival and angle of departure. Now what I mean by that is something that we are going to discuss right now with an example. Okay, let's discuss that with an example. So let's take an example. Okay, so let's have GSHS. Again, it doesn't matter what GSHS what GS and what HS are individually, but it matters that this is what GSHS totally has. So same, this is S times SS square plus 4S plus 6. All right. So say this is my GSHS. So again, I am going to draw the root locus of this, right? I'm going to draw the root locus. And as usual, whenever drawing the root locus, let's check out a graph paper. Okay, would be pretty easy. But before that, let's calculate the open loop poles. So it's a third order system, right? So number of open loop poles is 3. So that's the number of open loop poles. Okay, number of open loop zeros is 0. So that's the number of open loop zeros, right? And what are the open loop pole locations? So I have S equal to 0 already. So we are solving this equation, right? S times S square plus 4S plus 6 equal to 0. So again, if we solve this, we get S equal to 0 and 2 complex conjugate roots here, right? So S equal to 0, and we get S equal to minus B plus minus B square minus 4AC. So 16 minus 24 divided by 2A. So these are the roots here. So that's kind of becomes minus 4 plus minus, how much is it? Two divided by 2. So that's minus 2 plus minus j root 2. Okay, minus 2 plus minus j root 2. So that's minus 2 plus minus j 1.414 j root 2. Okay, so again, so I have 3 roots in total. So one of them is minus 2 minus j root 2, other one is equal to minus 2 plus j root 2. So these are the 3 roots, 3 open loop pole locations we have, right? So now let's bring out a graph paper and draw it. Okay, so let's bring out let's draw the axes first, and I hope this time around I would draw it nicely, which I didn't. Let's draw this. Again, mistake. All right. Hold on. So where are the open loop poles? So 0 minus 2. Okay. Okay, let's hope that this works. Okay, and if the drawing doesn't work, then we will figure out what to do next. Okay, so I'm calling this to be 1, calling this to be 1. So 1 2 3 4, calling this to be 1, this to be 2. Okay, so that's 1 2, that's 1, that's 2, Okay, sigma, and that's j omega. Okay, all right. So the open loop poles are at s equal to 0. We again constructing the root locus, try to figure out the thought process here. Okay, so s equal to 0, we have one open loop pole. So that's the location of one of the open loop poles. The others are minus at -2 plus minus j root 2. So they are going to be somewhere around here, right? Yeah, so somewhere around here and somewhere around here. Again, whenever you are drawing this, you would have a better graph paper than I do. And somehow my table is squeaking. All right, I have a squeaky table. So -1, -1, -2, -3. That's again s equal to 0. That's s equal to 0, right? So again, now let's figure out which part of the real line is on the root locus, right? Let's figure that out. The question is, if I have any arbitrary point here, if I have an arbitrary point here, and if I'm standing here and look to my right, how many open loop poles and zeros do I see? I see 1. So this is going to be a part of the root locus. If I'm standing here somewhere, okay, and if I'm looking to my right, and I would see 3 open loop poles and zeros to my right. So that way also, this part is going to be on the root locus. So this entire line is going to be on the root locus, right? So entire negative real axis is going to be on the root locus. So we figured something out right from the get-go. So let's do that. So this part of the real axis is going to be on the root locus. Okay, so that's fine, I think. So let's put the arrows properly. So again, definitely I think this root is going to go in this direction and go in this direction, right? Obviously. So I'm saying that the entire story starts at s equal to 0 here when k equal to 0, and then again this is s equal to minus here. This is s equal to -2 plus j root 2, and again here at this point again k is equal to 0, and this is at s equal to -2 minus j root 2, and again k is equal to 0. So the again the locus of the roots would start, locus of the closed loop poles would start from these open loop pole locations when the gain k is equal to 0. All right, so that's fine and all, but let's jump into rule number 3 and figure out possible breakaway and break-in points, right? Let's calculate the possibility of breakaway and break-in points. So we did that. So possible breakaway or break-in points. Okay, breakaway or break-in points. So we represent the equation in terms of k. So we have this. So again, the characteristic equation looks like 1 plus k gs hs equal to 1. So essentially k is -1 by gs hs. Again, as long as you are consistent with this, this would do. So all you can otherwise you could just write down the characteristic equation of the closed loop system essentially, and from there you could have proceeded. Same thing. Okay, so I would have k equal to minus s times s square plus 4s plus 6, s times s square plus 4s plus 6, right? And for possible breakaway and break-in points, del k del s would have been 0. So let's calculate that. So this is again, this is just minus s cube plus 4s square plus 6s. That's going to be minus 3s cube plus 8s, sorry, 3s square plus 8s plus 6. Someone asking. Oh, sorry. Yes, thank you. So of course the right hand side would be 0, right? And for breakaway breaking points, possibly this is going to be 0. So for possible breakaway or break-in points, del k del s has to be equal to 0. So we have this equal to 0. So let's get rid of the minus sign, because if we are equating something to 0, what's the point of having a minus sign overall, right? So you can so find that, I think, right? So that's equal to 0. So that's again a quadratic equation. So what are the breakaway break-in points? So minus b plus minus root over b square minus 4ac. So 4 minus by 2a. Okay, so that's gonna be minus 8 plus minus j, gonna be 8. So 2 root 2 by 6. So that's gonna be minus 4 plus minus j root 2 by j root 2 by 3. Okay, j root 2 by 3. Right, so we have two breakaway and break-in points. Okay, and since they are complex conjugate pairs, both of them will have to be true, otherwise the symmetry of the root locus will break. Rule number 1 will break. If one of them is a breakaway valid point and the other is not, the symmetry of the root locus will break. Because try to understand now as the story goes. Let me just get rid of the graph paper for a moment. Okay, see, one of the possible breakaway break-in points is here and the other is here. So both of them have to be true in order for the thing to be a valid breakaway break-in point. Now let's try to use our common sense here. What is a breakaway or break-in point? A breakaway or break-in point is a point at which more than two roots actually meet, right? Now unfortunately, what are the possibilities here? We already have seen that this root is possibly moving in this direction, right? This root is possibly moving in this direction, right? So that's one thing. So what are the possibilities? What are the other possibilities? The other possibility is that this root is somehow going to approach this point and this root is going to somehow approach this point. But the moment something like that happens, we have two violations. One violation is that the root locus is crossing itself. So the root locus is crossing itself, right? And the other violation is that the symmetry has been broken. Okay, the root locus is no longer symmetric. The same would happen if this is a valid breakaway or break-in point. Okay, since this cannot jump from this somehow, because this is already going in this direction, the roots will have to go in this direction and this will have to somehow approach this. Again, two rules would be violated, that the root locus is crossing itself, number one, and the root locus is no longer symmetric. All right, the root locus is no longer symmetric, because at this point they will have to break away again, right? Break away from this, something like that. So the root locus is not going to be symmetric. So this is going to inherently break the symmetry of the root locus. But also keep in mind that in order to preserve the symmetry, this will also have to be a valid breakaway or break-in point, otherwise symmetry will not be valid. So I have to break in once more, something like that, and then break away. So this is going to be a complete and utter mess, right? So that's not going to be a valid breakaway or break-in point. Okay, so I think you got this. And also you could just calculate the angle criteria. You would see it's not going to be a valid breakaway or break-in point, because it's not going to give you an odd multiple of 180 degrees, because that would be the simpler explanation here. Okay, so let's get rid of all this. All right, so this is not a valid, just let's write this is not a valid breakaway or break-in point. Not valid, rather I would say not valid, since these would break the symmetry of the root locus. Let me write down the proper reason, and of course you can verify that by using the angle criteria. This would break the symmetry of the root locus and make it inter intersect with itself. All these are illegal. Okay, this cannot be true. So none of the breakaway or breaking points do work here. Okay, so we don't have any breakaway or breaking points. So let's look at rule number 4 and j omega axis crossover, right? So now let's look at possible j omega axis crossover. Okay, again we are saying possible, right? There is always the possibility that it's not going to be possible. Just hold on for a second. All right, so how do I check for possible j omega axis crossing? Very simple. Let's write down the characteristic equation. So what is the characteristic equation? Of course, this is GSHS, right? So, and of course, if you just simplify this, this is going to be the characteristic equation going to be this plus k, right? Right. So the equation is the characteristic polynomial of the closed loop system would be s times s square plus 4s plus 6 plus k. Anytime if you have any confusion, just ask s cube plus 4 s square plus 6s plus k. Again, our intention would be to force a force a difficulty 2, right? So let's construct the route table, right? So I would have s cube row, s to the power s square row, s1 row, s0 row. So this is 1, this is 6, this is 4, this is k. So that's going to be 24 minus k divided by 4, and we have a 0 here, and this is going to be k. Again, we can force a difficulty 2 by making this one 0, right? So I would say difficulty 2 would arise if k is equal to 24. So if I choose k to be equal to 24, then there will be a difficulty 2 in the construction here. So if difficulty 2 arises, then this becomes the auxiliary polynomial. Okay, so the auxiliary polynomial becomes 4s square plus k, okay, which is 4s square plus 24, and the roots of the auxiliary polynomial are the points at which the j omega axis crossover happens, right? So essentially the points are so the roots of this auxiliary polynomial would be points on the j omega axis at which this crossover would happen. So essentially we can solve this. The points of j omega axis crossing, rather j omega axis crossover, are given by just solve this equation. 4s square plus 24 equal to 0. So that's going to be s equal to plus minus j root 6. All right, plus minus j root 6. So what are the points here? Plus minus j root 6 we are saying. What is the value of root 6? Let's take a calculator. What is root 6? Okay, square root of 6. That's 2.449. Okay, 2.449. So these are, let me bring out the graph paper once more. $2.449, right? Okay, so j omega axis crossover is happening somewhere here. So I would say somewhere here and somewhere here, right? So these are the points at which the j omega axis crossover would happen, and we also know the gain at which the j omega axis crossover would happen, right? So we know the gain because the gain k is 24 at that point. So I would just say, just write these down. So here the j omega axis crossover would happen, and happily at this point, so s equal to plus j root 6 at this point, and correspondingly the gain k is equal to 24 at this point. Okay, all right, and this is going to be -1 here, minus j root 6, and the same gain here. And let's just bring squiggly lines to make sure that we point to the same correct thing, right? All right, so let's get rid of that. All right, so these are the j omega axis crossover points here. All right, so we figured that out. Of course, you would see that there won't be any circular portions here. Again, that'll be evident once we calculate the asymptotes. Now we have 3 open loop poles. So what are going to be the asymptotes here? How many asymptotes am I going to have? I'm going to have 3 asymptotes. So let's calculate the centroid and the asymptotes, right? Let's calculate the centroid and the asymptotes. Centroid. Let's calculate the centroid. So centroid would be a real point on the real axis, where this is calculated by sum of the open loop poles minus sum of the open loop zeros divided by number of open loop poles minus number of open loop zeros. Now what is the sum of the open loop poles? So what are the open loop poles again? So open loop poles are at 0, -2, minus j root 2, -2 plus j root 2. So if you sum them up, you get -4, right? And there are no open loop finite zeros, so that would be -0. So we have -4 minus 0 divided by how many open loop poles did I have? 3. How many open loop zeros did I have? 0. So that's going to be -4 by 3. So minus 1.33. So that's going to be the location of the centroid. So just mark it. Let's just mark it here. Okay, let's calculate the angles of the asymptotes. So how many asymptotes am I going to have? I'm going to have 3 asymptotes, right? I'm going to have 3 asymptotes. So let's write. So this is the number, right? P minus n. So therefore there would be, so this is the number, right? P 3 minus 0. 3 asymptotes originating from sigma equal to minus 1.33 with angles. So these are the angles. So divide 180 degree accordingly. So it's going to be 2n minus 1 divided by p minus z times 180 degrees, right? So again, n is equal to 1, 2 and 3. So that's going to be 2, and then so let's write it down. Okay, 2 minus 2 minus 1. So again, that's 3, right? Times 180 degrees, and the other one would be 2 times 3 minus 1 divided by 3 times 180 degrees, right? So again, or these degrees, right? So this is going to be 1 by 3, so that's going to be 60 degrees. So this is 3 by, so that's going to be 180 degrees, and that's going to be 300 degrees, right? So these are the asymptotes. So let's mark this now. Okay, so the centroid is located here. The centroid is located at minus 1.33. So this is minus 1.5. So this is minus 1.5. So somewhere here. So this is the location of the centroid. And from the centroid, we have the asymptotes, right? And one of the asymptotes is at 180 degrees. So essentially, one of the asymptotes we already know about, right? So we already know about one of the asymptotes because this is one of the asymptotes, right? And we already have a route that follows one of the asymptotes, right? So we already have a root that actually follows one of the asymptotes, so we are in good shape there. So that is one of the asymptotes. Okay, is it visible? Hardly visible, right? So that's going to be one of the asymptotes. Okay, all right. And what are the other asymptotes? The other asymptotes are going to be at 60 degree and at 300 degree. And how do I calculate the 60 degree here? Using the same idea that this length from the centroid, this is 1.33, this is root 3, right? This distance is not root 3, I think, so 4 by 3, that, so this distance is 1.33, right? So again, how do I draw a line that's 60 degree? Okay, by calculating where it intersects here. Okay, and how do I calculate that? Just take the tan, right? So 1.3 tan 60 degree. So this point here on which the asymptote will break away here. So let's just calculate that as a rough calculation here. So 1.33, so it would be 1.33 tan 60 degree, and tan 60 degree is root 3, so tan 60 degree is root 3, so 1.33 root 3, so how much is that? That's 2.3, right? So 2.3, so 2.3 would be just below this, so 2.3 would be just below this, so somewhere here and somewhere here, right? 2.3 would be just below the points from which the geometric axis crossover is happening, right? So we have our calculation here, so we can now draw the angles. So this is going to give me a 60 degree asymptote here. Okay, and this is going to give me a 300 degree asymptote here. Again, everything is symmetric about the real axis. That's the whole point here. All right, and we have just above that the point at which the geometric axis crossover happens. All right, all right. Now comes the interesting part. So I know already that one of the roots are following one of the asymptotes, right? And again, since there are no open loop zeros, I know that this root will have to follow this asymptote. Okay, this root will have to follow this root will have to follow this asymptote somehow, right? This root will have to follow this asymptote, and this root will have to follow this asymptote, right? So that is something we already know, because that's gonna happen anyway, right? But how? Okay, because I could have drawn something like this. I might as well draw the root locus that kind of looks like this. Okay, I could say, okay, they are going to start from here and then they are going to follow the asymptotes like this, and let's draw it symmetrically about this. It is going to start from here and then it is going to follow the asymptotes like this. Okay, whatever it is, let's draw a symmetrical drawing. Okay, so we can draw something like that, and we can say, okay, fine, that's how the roots are going to follow, right? But who is going to stop us from drawing something arbitrary like that? Answer is the angle criteria once again. Okay, so instead of drawing something arbitrary like that, the angle criteria would tell me how the root locus would depart from the complex conjugate poles. So this is a complex conjugate pole, this is a complex conjugate pole, so together they make one complex conjugate pole pair, and the angle criteria would dictate how the root locus would depart from the complex conjugate pole pair. So would it depart like this? 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 Anyway, how this would depart from the complex conjugate pole pair would be dictated once again by the angle criteria, because angle criteria needs to be satisfied, and then if it is satisfied, then we can always satisfy the amplitude criteria, magnitude criteria, right? So okay, so the angle of departure would be entirely dictated by the angle criteria. I think this is understood, right? So now let's look at this, okay, and let's figure out how the angle criteria would be upheld somehow, okay, and what angle, and if it at what angle if it departs, what angle of departure would satisfy the angle criteria, right? Do you understand my question? Yeah. Okay. So angle of departure essentially makes sure that a root locus departs from a complex conjugate pole pair in a fashion that satisfies the angle criteria. Otherwise, it won't be a correct one, right? So with that said, let's figure out how we can do that. So in order to do that, we have to zoom in on this figure at this point. Okay, let's take this figure and imagine we are zooming in on this figure around this. We are zooming in around this. Okay, we are zooming in around this. Okay, let's just draw a box here in which we are going to zoom in into that. Okay, so that was our complex conjugate pole. Just keep in mind, so we have zoomed in around this. Okay, so imagine we have zoomed in quite a lot. Okay, again. All right. Okay, just keep in mind. So now we are taking, so we are trying to find out the angle at which the root locus departs from the this complex conjugate pole, right? And if we know the angle at which the complex conjugate the root locus departs from here, and if you can draw the root locus in this section, then we would be also able to draw the root locus in this section, because the root locus is symmetric about the real axis. So if you can do it above the real axis, we will be able to do it on the below the real axis. We won't have to do any extra calculation for that, right? So now let's consider the departure here. Okay, consider the departure. Again, I said this is a zoomed in version, right? This is a zoomed in version of this pole, right? So now let's say the root locus departs from a certain angle here, whatever angle this is. Let's just say, and again, I am intentionally taking a wrong example. I'm intentionally drawing it wrong. Let's say the root locus departs this way. The root locus is departing this way. Let's say that. Okay, let's say the root locus is departing this way, and then they would merge like that. Let's say that. And again, I am intentionally drawing it the wrong way, because you would see, if your calculations are correct, automatically your wrong drawing would be corrected. Okay, let's say that. Okay, and with that drawing, if I say the root locus is departing that way, and if I zoom in here, I would see a straight line up going from this, right? I would see a straight line going from this, isn't it? The earth looks flat because at a time we can only see a very small portion of the earth, right? Just like that, this would look like a straight line if I zoom in like that. I think that's understood, right? So with that said, so that part looks like this, right? No confusion, I think. All right. So it has departed, it would depart this way. I'm imagining, okay, again my imagination is wrong, and I am taking a point very close to this, okay, and zooming in on the figure. If I zoom in on the figure, I would see that this point kind of looks like to be here. Okay, this point kind of looks like to be here, and this part here looks like a straight line. I think that's obvious here. Okay, let me know if this is not obvious. Okay, now this point that I'm drawing here, which is close to this point, is actually very close to the pole here, very close. Okay, just after the departure. Okay, just after the departure. So these two, this green one and this red one, are very close together, right? That is how zooming in makes it look like a straight line, right? Imagine they are very close together. All right, so essentially, even though in the zoomed in figure I'm drawing the point to be somewhere here, actually if you look at the zoomed out figure, okay, hold on, let me just get rid of that. Yeah, so even though in the zoomed in figure I am drawing the point here, in the zoomed out figure I would see that the point is almost indistinguishable from this pole, right? The point is so close, say for example somewhere here, very close to it, right? Very close to it, something like that. All right, no issues. Let's figure out the angle contribution now. Okay, someone is saying, can I repeat this part? Okay, I am imagining the root locus to be something like this. Root locus to be starting from here and going that way. Who is going to stop me from drawing something like that? The answer is the angle criteria, of course. And in order to figure out the angle at which this departs, so what is the angle at which this departs? So this is the angle of departure, right? This is the angle at which the root locus is departing, right? But really this is not that good of a way of doing this, because I have to zoom in on this figure here. Okay, I have to zoom in on this figure to figure out the angle of departure, the exact angle at which the root locus departs from this complex conjugate pole here. That's the angle of departure. So we are zooming in on the figure here and we are drawing it like that. So this is a zoomed in figure, and here this is the angle of departure. Okay, and again this curve here after zooming in would look like a straight line, right? Would look like a straight line. I think that's understandable, right? So this is very close to the original point. All right. So again, this is so close, but after zooming in, it looks like this. Again, the angle is this, the angle of departure, angle at which the root locus departs. So if I draw it like this, then this is going to be the angle of departure, right? We always measure angle with respect to the horizontal positive real axis. Okay, so something like that. But if I don't have a zoomed in figure, then this point would be indistinguishable. So let me even though that is true, let's just draw the point here. So this is the point we have been so this point is identical to this point. All right, so that's fine, I think. All right, now let's measure the angles. Let's measure the angles, because we are trying to satisfy the angle criteria, right? We're trying to satisfy the angle criteria. All right, got it? Now how do I figure out the angle contributions here? Again, we try to draw the lines here and figure the angle criteria. Let's do that. Let's do that. Okay, now let's take a thinner line. Okay, so what is the angle contribution of this pole? What is the angle contribution of this pole on this point here? What is the angle contribution this? So we have to just draw this line, right? We have to just draw this line. We have to just draw this line here. All right, we have to just draw this line, right? And this angle would be our θ1. Got it? Then we would have to draw this line, and this angle would be, and this angle would be θ2, and then try to understand. So this is the angle contribution of this point, this pole, right? This is the angle contribution of this pole. This is the angle contribution of this pole. So θ1 is the angle contributed by this, θ2 is the angle contributed by this. But what is the angle contributed by this? What is the angle contributed by this pole? Because these 2 points, this pole, open loop pole, and this green point here, they are distinct from one another, right? So this will also have to contribute certain angle here, right? They will have to satisfy certain contribute certain angle. But what is that angle contribution? That's this one. Because now if I zoom in, I would see that this pole here is also contributing an angle to this point here, and because every pole with pole and zero would contribute certain angle here, right? And what is the angle here? The angle is θd itself, because if I draw lines like that, okay, if I draw a line towards the horizontal x-axis, horizontal real axis, and then I draw a line joining this pole to that point, then that would make an angle θd. Then θd would be the angle contribution here. Okay, but if I draw it like this here, the angle contribution kind of looks like this. Okay, something like that. So that's the zoomed in drawing here. So that's your θd, right? Sort of. All right. All right, I think you people got this, right? So that's the angle contribution of this entire thing. Yes, now we are going to do an approximation. Now we are going to do an approximation. What approximation? The approximation is that this green point here and this red point here, they are very close, and as such, magnitude wise, they are indistinguishable from each other if I have zoomed out. So this theta 2 is almost approximately 90 degrees. Is almost approximately 90 degrees. Approximately, I'm saying, right? Okay. Now what about theta 1? How do I calculate theta 1? Theta 1 is this angle. Okay. This entire angle. But what is this angle? I can calculate this angle if I know this angle. But how would I know this angle? I can know this angle because I know this distance. What is this distance? This distance is 2. And what about this vertical distance? This vertical distance is √2, right? I know that. So tan inverse perpendicular by base would give me this angle. And once I know this angle, I can subtract it from 180 degrees. I would get that angle. So theta 1 would be 180 degree minus this angle. Okay. And what is this angle? This angle is tan inverse. This angle is tan inverse. This perpendicular by base. I know this length of the perpendicular because I know this point, right? This point is -2 plus j√2 essentially. So this height is √2 and this is 2. So we have tan inverse √2 by 2. Okay. So let's again take the help of a calculator and figure this out. Okay. Let's figure this out. So we're saying A10. So A10, this is going to be A10. You can do it yourself, right? A10 1 by √2. That's going to be 35 degrees approximately, 35.3 degrees. 35.3 degrees, right? So this is going to be 35.3 degrees. So approximately this is 180 degrees minus 35.3 degrees. 35.3 degrees. Okay. All right. Fine. I'm not subtracting it just yet. Okay. Approximately that, like that. Again, try to verify that yourself. So this is the angle contribution here. This is the angle contribution here. And this is theta d. That's the angle contribution. So we know all the angle contributions, right? All the angle contributions. So I am saying now, this is the thing. Angle of departure. See, I did not do the calculation because of a reason. Departure from -2 plus j√2. Angle of departure from that. Okay. So theta d plus, so total angle contribution. So minus theta d, of course, because these are poles, right? These are poles. I would have a minus sign inherently because we already know this, right? Let's go back to this, because poles do have negative angle contributions because of all these minus signs, right? Right, because they are in the denominator, so they have negative angle contributions nonetheless. So all the angles will have a negative sign prefixed to them. So this is minus theta d minus theta 1 minus theta 2, and that will have to be some odd multiple of 180 degree. Any odd multiple of 180 degree would do. Essentially, if it's 180 degree or 180 degree plus any multiple of 360 degree or subtract any multiple of 360 degree, it would do, right? So that is what we have. So only theta d is unknown here. I do not know theta d. Okay, but I know theta 1 and theta 2. So let's write that equation. So minus theta d is unknown. But what is theta 1? I already have theta 1. So theta 1 is 180 degree minus 35.3. That's 180 degree minus 35.3 degree. right? And what is theta 2? That's 90 degrees. So that's minus 90 degrees. And that has to be any odd multiple of 2n plus 1, 80 degrees. Now, odd multiple of 180 degree, right? This could be plus 180 degree, this could be minus 180 degree, right? Right? It could be plus 540 degree, it could be minus 540 degree, any, right? Any odd multiple of this would do. So we would pick and choose according to what result I am having here. So let's see what gives us the most suitable calculation here. Theta d, because you understand, right? 180 degree and 540 degree are the same thing. 180 degree and minus 180 degree are the same thing, right? Minus 540 degree, 180 degree, plus 180 degree, minus 180 degree, plus 540 degree, minus 540 degree. All these things are the same thing because they are just odd multiples of 180 degree, right? With an angle, you can just add or subtract 360 degree at your will. Nothing will change as per the geometry is concerned, right? So this is minus 180 degree, minus 35.3 degrees, 35.3 degrees, minus 90 degrees. And let's just say for my convenience, okay, let's just keep it like that, 2n plus 1, 180 degree, right? I would choose whatever suits me best. So this is minus theta d, and this becomes equal to, try to understand, 180 degree. So I'm bringing all this to the right hand side, plus 90 degree, okay, plus 35.3 degree. And let's just say I am choosing this to be minus 180 degree, because that is something I can choose, right? I'm choosing this to be minus 180 degree because any odd multiple of this would do. So I'm choosing this to be minus 180 degree. So just keep that in mind. I can choose whatever it is, right? Because in any case, if you don't choose it minus 180 degree, if you choose it to be plus 180 degree, you're just adding 360 degree to it, right? The same thing. You just make one round and come back to the same thing. I'm choosing, right, particularly because I want this to be cancelled out. Again, that's just a part of the calculation here, right? So I can cancel this 2 out. So I have minus theta d equal to this angle, right? Minus theta d equal to this angle. Now what is this angle? 125.3 degrees, right? Right? Alright. So please let me know if you understand this. Oh, sorry. That has to be a plus. Sorry, that has to be a plus. Oh, thanks for correcting the problem here. So there has to be a plus sign, right? So there is a minus sign. Yes. So you can see I am very good at calculating things. All right. So that 180, that's 180. So that's 90 minus 35 degrees. So 35.3 degrees. Right. So I have changed this to the plus sign and bringing everything to the right. This gives me a negative 180 degree, positive 90 degree, and then negative 35.3 degree, and then minus 180 degrees, right? Thank you for correcting this. Okay, so 90 degree minus 35.3 degree. So let's calculate that. 90 minus 35.3, so 54.7. So that's 54.7 degree, and of course that's minus theta d. So theta d would be minus 54.7 degrees. Okay, minus 54.7 degrees. So what did I just understand here? That the angle of departure has to be minus 54.7 degree. Yes, someone is saying instead of 180 minus 180 degree, if I choose something else, if you choose plus 180 degree, what would happen? You are essentially adding 360 degree with this, right? So it would not make any difference as far as the geometry is concerned, because if you have theta angle at 360 degree, you still get theta essentially as far as the geometry is concerned. also the planar trigonometry is concerned, right? So instead of adding this, if you say plus 180 degree, then this won't cancel out, and instead this becomes plus 360 degree combined with this. So it doesn't matter, you can add as many 360 degrees you want, you can subtract as many 360 degrees you want. I'm just trying to keep the angle below angle between minus 180 and plus 180, right? There is no point of writing this as this plus 360 degree. It won't make any difference. So as the answer goes, I'm trying to keep it within minus 180 degree plus 180 degree, right? We can understand that, right? Because if I say 300 degree, what is 300 degree but minus 60 degree, right? 300 degree is nothing but minus 60 degree, right? So yes, that is how I'm writing it, right? Again, it's entirely up to you what angle you are trying to write. But now look very carefully that we have figured out theta d to be minus 54.7 degrees, right? Now think about that, minus 54.7 degree. How would theta d look like, right? So this angle where we had drawn it this way, this angle theta d here, this was a positive angle, right? But in reality, so for example, if the root locus did start like this, I mean, then this angle would be something like a positive angle, right? The angle of departure would have been a positive angle like that. That could not happen. That could not happen because we already found that theta d is minus 57 point. So minus 57.3 degrees, whatever it is. How much is it? Minus 54.7 degrees. That's a negative angle. Negative angle. So in reality here, theta d will have to be a negative angle. Okay. So that is how I started drawing it incorrectly, to especially tell you how this thing really works. So let's get rid of this chunk from here. Okay, hold on, get rid of this chunk. Okay. You understand the point? That's enough, I think, for me. Okay, now let's construct the proper theta d here. Okay, so now we know that the theta d would be such that it would be minus 54.7 degrees. So this would not depart in this way, but instead, if I zoom in here, in reality, the departure would look somewhat like this. The departure would look somewhat like this, right? Of course, with respect to the horizontal x-axis. So this is going to be minus 54.7 degrees. Of course, if we take angles in the clockwise direction, this becomes a negative angle, right? That's going to be the departure. So truly speaking, we now know how this would depart. So this would depart in this way. So that's the angle. And of course, after that, we know the rest. What rest? We know that as the gain increases, the root locus will follow along the j omega axis, the asymptote, and cross over the j omega axis into the positive part of the S-plane. So that's going to be the root locus here. So we now have this angle. So we know that the angle of departure, okay, the angle of departure is minus 54.7 degrees approximately, right? And just like that, if we have this drawing here, then of course the other thing here would be just a mirror image, right? Now drawing this and drawing a mirror image kind of is pretty difficult on this. Again, I'm trying my best, you have to understand that. You can just type in any question that you might have got already. Yeah, something like that. Again, if this is minus 54.7 degrees, then this is going to be plus 54.7 degrees and all, right? So you don't have to write that. Again, this has to be a proper symmetric drawing, which I couldn't draw but you can if you're doing it on pen and paper, right? So again, as k goes to infinity, these roots goes to infinity as well, following along the asymptotes. So as k goes to infinity there, so again it starts like that, right? So that's the end of the root locus for this one. That's the end of the root locus for this one. So that's the angle of departure from complex conjugate poles. Okay, somebody said yes, it is always, root locus is always symmetric. That's your rule number one. Root locus is always symmetric about the real axis. It will have to be symmetric. The root locus itself will be symmetric always, always, right? Because what are you doing? What is the root locus? Essentially, you are solving a polynomial with real coefficients, right? And the roots or the solutions of a polynomial with real coefficients are either going to be real or complex conjugate pairs. So either the solutions are going to be on the real line or they are going to be complex conjugate pairs, right? And complex conjugate pairs are equally spaced apart from the real axis. So that way, root locus is always going to be symmetric about the real axis, always. Okay, so that's about it for the theories that you need to know. Again, angle of arrival, whenever you are talking about angle of arrival, you would have to do a very similar thing. Okay, and again, if you have zeros, then the angle contributions become positive because zeros are on the numerator and as such. So there will be certain worked out examples for you, so you'll be able to check those. Yes. All right. All right. So let's take another example. Okay. I know how to construct an example. So again, this is going to give you angle of. So let me just write down the thing. What did I write? Angle of. So let me just write down the rule here. Angle of departure. If the angle of departure from complex pole is theta d, then minus theta d minus sum of theta p plus sum of theta z has to be an odd multiple of pi, where theta z, sum of theta p is the angle contributed by the poles and theta z are the angle contributed by the zeros, right? Because zeros are in the numerator, they would have positive angle contribution. Okay. Okay. So let me just write it down here. Similarly, it will be for angle of arrival here. All right. So let's do one problem on angle of arrival. So I would construct the drawing first and then I shall give you the transfer function. Okay, because in my mind, if you give me a so if you just give me locations of the open loop poles and zeros, in my mind I can kind of construct the root locus, sort of. So I kind of know how to choose. Do I take a new page? I think I would take a new page. Okay, all right, so let's take this one. Okay, again, I'm trying my best to come up with an example. This has a possibility of going severely wrong, but let's still try anyway. I like to try things. Alright. Okay, let's say the open loop poles, one of them are here. Let's say one of them are at -1, the other is at -3. Okay, and I have two open loop zeros as well, so there would be no asymptotes in this example. I would have two open loop zeros as well. So let's say they are here. These are open loop zeros, for example. So the root locus would end here. This is one open loop zero, and this is one open loop zero. Okay, and as such, our example would have a question like this. So our example would have a question like this. So our GSHS would be, so I have two open loop zeros, right? So -1 minus a, so SA square is plus 2 2, and here I would have SA square, hold on, SA square yes. All right, so that's your example, so that's your question. Okay, so that's it. So essentially, if I draw it, it would kind of look like this. So you would have a comparator here. Okay, and this is the gain block. As the gain increases, the closed loop poles would also change their locations, and this is the transfer function. Again, some part of this could be on the HS as well, because I am only interested about GSHS, right? I think you people understand this by now. Okay, again, ask any question that you might have. Hold on for a second. How many messages am I getting? sorry for that. Anyway, so I have this transfer function. So I know that number of open loop poles is 2, number of open loop zeros are 2. So there would be no asymptote or no question of centroids or anything like that. Okay. And what are the pole locations? Pole locations are to be the solutions of this. And if I solve this, so I would get pole locations to be -1 and -3. All right. And the zeros would be at s equal to, these are the zero locations. So zeros would be at s equal to -1 plus j1 -1 minus j1, because I just constructed the problem that way. Okay. So the root locus would start at the open loop poles for k equal to 0 and end at the open loop zeros and end at the open loop zeros for k tending to infinity. Okay, so we understand that already. So we know that the root locus are going to start from these 2 points and they are going to eventually end up there. So of course there has to be some sort of a breakaway point or breaking point. So let's start drawing this already, right? So let's apply rule number 1. We know it has to be symmetric about the real axis. Rule number 2, what parts of the root locus are on the real axis? Okay, so is this portion on the real axis of the real axis on the root locus? No. Is this portion of the real axis on the root locus? Yes, because if I'm standing here, look to my right, I see 3 poles and zeros. Okay, so this part is going to be on the real axis. Is this part on the real axis? No, because if I stand here, look to my right, there are 4 poles and zeros, which is an even number. So this part is not going to be on the root locus. So this part of the real axis is going to be on the root locus. Application of rule number 2, right? Okay. Now let's talk about j omega axis crossing. You can verify that there would be no j omega axis crossing because you would not be able to force. You will not be able to force difficulty 2 in the Routh-Hurwitz table. So so your objective would be to verify these things, verify the claims. Okay, I'm just not doing those because I know that these are not going to happen. So verify that there, so number 1 objective for you, there would be no j omega axis crossing. You would be able to verify that. Okay, there would be no j omega axis crossing and you would be able to verify that. Okay, because you won't be able to force any difficulty 2 situation, nor you'd be able to make the system unstable by choosing a value of k. Okay, so verify that the closed loop system would never be unstable. Never be unstable. Again, you can verify all these things using the Routh-Hurwitz table, right? Routh table. You can verify those. Okay, no issues whatsoever. Understood, I think. Now let's do the next thing and check for possible breakaway or breaking points. Okay, so let's write down the equation. Let's write down the characteristic polynomial here, characteristic equation here. So the characteristic equation, so again the closed loop transfer function, if I say so, would essentially become k times s square plus 2s plus divided by s square plus 4s plus 3 s square plus 4s plus 3 plus k times s square plus 2s plus 2, right? So again, this is the characteristic equation and equate it to 0. So the characteristic equation is this. Again, you have to use this characteristic polynomial in for this, okay, for the Routh table. So that's equal to 0 and Of course, from that I know k is equal to minus s square plus 4s plus 3 divided by s square plus 2s plus 2. And let's equate del k. So let's calculate del k del s. Del k del s is minus, again I really don't care about the minus sign, but let's just keep it. So s square plus 2s plus 2 times the derivative of this, so that's 2s plus 4 minus s square plus 4s plus 3 times the derivative of this, so 2s plus 2, and of course a square there. Okay, so for breakaway or break in points, del k del s equals 0, so which implies that this equation equals 0. So again the numerator of this thing would be equal to 0, right? So this numerator would be equal to 0. Again I have just disregarded the minus sign. All right, so that's equal to 0. Okay, let's simplify this. I don't know how well the simplification would go. Let's just do one more trick here. So s square plus 2s plus 2, so that s plus 2. Again, just kindly properly follow along with the calculation because I'm really good at it. And s plus 1, that's equal to 0. So that's so s cube plus, so I have 2s plus 4s, that's 6s. Sorry, s not s cube. Yeah, let's just write everything out. Okay, so let's write s cube plus 2s square plus 2s plus 2s square plus 4s plus 4 minus s cube plus 4s square plus 3s plus s square plus 4s plus 3, that's equal to 0. Okay, all right, so I see that s cube cancels out. Okay, what about s square? I have 2s square, 4s square minus 4s square, so minus 4s square. Okay, 2s square, 4s square minus 4s square, and then plus s square, so that's just s square, taking care of that. So 2s 6s minus 3s, so that's 3s and minus 4s, so that's just s minus s, I think so, right? So 2s 6s 6s minus 3s 3s and minus 4s, so minus s. And what the constant term? 4 minus 3, so that's 1. Okay, all right, now which implies right now is that I have to solve this in order to get the, so this is going to be plus 1 minus b, that's minus b essentially, plus minus b square, so that's 1 minus 4ac. Did I make any calculation mistake? It seems like I have. Can someone verify? There has to be a breakaway or breaking point, right? Okay, why did I make a mistake? Yes, there has to be a minus sign. Man, I'm really good at calculating things. Please verify that, verify if I have made any other mistake. Yeah, because I can see that there has to be a real breakaway point, right? There has to be a real breakaway point between -1 and -3, but I couldn't see that with this calculation. So this is s square plus s minus 1 equal to 0. Yeah, Okay, that's not matching. What about the next term? That's 2s plus 4s, 6s, and I think it's minus 7s, so that has to be minus, right? So please verify that whether this is the correct one. Please someone verify that, and if this is the correct one. I might get something terribly wrong here, unfortunately. That's why I always use a computer or a calculator while doing this. I might just have made a mistake here. Okay, this is correct, right? Okay, fine, thank you. So s equal to minus b plus minus root over b square minus 4ac. So I have 1 plus 4 divided by 2a, that's 2. Okay, so it is minus 1 plus minus root 5 divided by 2. Okay, wow, feels like golden ratio, rather smells like golden ratio. Anyway, so just calculate this. Minus 1, again, just we can say that there are two roots, right? Minus 1 this, minus 1 plus this, and minus 1 minus root 5 by 2. Again, I'm discarding this, right? Okay, can I discard this? I think I have to discard this. Okay, just calculate these values. Bring up calculator. So switch to the screen. So this is minus 1 plus square root 5 divided by 2. That's 0.61. That's 0.61. 0.618. Okay, that's again 0.618. That's kind of the golden ratio here. Okay, lol. And this is minus 1, right? So I could have discarded that, right? That's minus 1.618. Minus 1.618. Yeah, so this is discarded. This is discarded. Why? Because this is a positive, this is s equal to 0.618, and that's not part of the root locus. 0.618 is somewhere here, and this is not part of the root locus, right? Because of the angle criteria, once again, because of rule number 2. So that's discarded, right? And we have another one at minus 1.618. That's part of the root locus because this is B2, this is here, right? Minus 1.618 would be here, right? Minus 1.618 is going to be here. So with that said, this is going to be a part of the root locus. This is going to be the part of the root locus. So this is a valid point. So this does not satisfy the angle criteria. Not part of the root locus. But this is okay. So this is a valid breakaway point. So you have a breakaway point. Of course, we have to have a breakaway point. Otherwise, how would it work really? Oh, sorry. What did I draw? What am I doing? I think somehow my brain is not working. This is minus 1.618, right? Okay, let's take the graph paper out. All right. Okay, minus 1.618. So minus 1, minus 1.5 is here, minus 1.6, 1.75 is here, minus 1.6, it's somewhere here. All right. All right, so we have got the breakaway point here. So the roots are going to approach in this direction and in this direction. So again, as the story goes, the root locus is starting from this location and this location when k is equal to 0. So s equal to minus 1 when, so s equal to minus 1 when k is equal to 0, and again s equal to -3 when k equal to 0. So the root locus will start from these 2 points. They would approach each other and they would meet at this breakaway point. Okay, this is the breakaway point, obviously. Okay, and we know this is s equal to -1.618. But what is the value of the gain? Because the moment I can satisfy the angle criteria, I can always satisfy the magnitude criteria, right? Let's calculate the gain k. Okay, and how do I calculate the gain k? Simply, I know that the angle criteria and the magnitude criteria tells me that 1 by k will have to be mod GSHS. That's the magnitude criteria, and from that I can actually calculate the gain, which is 1 by k equal to mod GSHS at this point. So again, what is GSHS? GSHS is this enormous transfer function. What was it? Hold on. Yeah, GSHS is this thingy. Take the happy mode of that, and here on this put s equal to -1.618. just put the value and take the reciprocal. That will give you the value of k. So can somebody tell me the value of k? On this put s equal to -1.618. calculate everything, take a mod on the whole thing, and get a reciprocal. Please do that. I do not trust myself with calculations. Okay, so have you figured out? So I think you have some confusions. Huh? So please figure out the calculations. So Python is the best calculator one can have. Okay. All right. All right. All right. All right. And absolute value of that is 0.618. 0.618. Wonderful. So k is 0.618. Again, usually, of course, Python is the best calculator, right? Okay. So we have done calculating that. Reciprocal. We have to take a reciprocal. We have to take the reciprocal. because that's 1 by k, right? So k is 0.618 when that happens. So I know that the two roots would be equal, and the breakaway would happen at k equal to 0.618. That's wonderful. That's kind of the beauty of golden ratio. Whenever the golden ratio appears somewhere, it pretty much stays throughout the story of that particular incident. And now they would break away from this, and we also know the angle of breakaway, right? What angle will they break away with? Of course, the angle of breakaway here would be 90 degrees, right? So that's again in the rule of breakaway and break-in points. So this root will break away in this direction, this root will, one of the roots will break away in this direction, right? And they would approach this, right? As k tends to infinity, they would approach this. Now what angle at which, what would be the angle of approach, right? As k goes to infinity, they will approach this. But what is the angle of arrival at open loop zeros? What is the angle of arrival? Okay, because I know from the rule of the breakaway that this is going to break away at 90 degrees, but this could have just approached this in this way. That could have happened. As long as the symmetry is preserved, no other rules are being broken, except for the rule of the angle criteria, right? So the angle criteria would preserve what angle at which the roots arrive at the open loop zeros. So again, you have to verify that there are no asymptotes. So your objective would be, since there are equal number of poles and open loop poles and zeros, so verify, I say, that there is no centroid or asymptote. So those calculations are again gone. Okay, so let's calculate the angle of arrival at this arrival, right? Let's calculate the angle of arrival. Okay, before we do that, okay, let's calculate the angle of arrival. Arrival at s equal to -1 plus j1. So the complex conjugate complex 0 on top, right? So at when k tending to infinity, the angle of arrival. So we are going to do the same calculation here. So in short, we are going to assume a point here, okay, and zoom in, try to figure out the angle. Again, we have two poles here, right? One will contribute certain angle, this one will also contribute certain angle here, right? So let's draw those for the moment. So what angle will, so again, the point that I'm talking about is at the very close vicinity here, right? So this is going to be the angle contribution here. So that's going to be 90 degree, okay, and this is going to be the angle contribution here. So that's something we can calculate, okay. And the angle of arrival here, that is going to be a positive angle because that angle is contributed by the 0, right? The angle of arrival is contributed by the 0. So I would say the angle of arrival rule, I would say if the angle of arrival at a complex 0 is theta a, then of course that's the angle contribution by that complex 0, right? Then theta a would be then plus theta a, okay, minus summation of all the angles contributed by the poles plus summation of all the angles contributed by the zeros. That has to be an odd multiple of 5. Okay, so now let's go back to this discussion, and this time around I would just copy this drawing. Okay, I do not want to make this a mess, right? Let's copy this drawing instead. Okay, so we are calculating the angle of arrival here, right? The angle of arrival here. So we are going to choose a point very close to this, and let's calculate the angles. Okay, so what about the angle here? What about the angle contributed by this? So that's approximately 90 degrees, right? That is approximately 90 degrees, because this point is here at a very close vicinity to this, right? So this angle is approximately 90 degrees. Okay, so you are calculating the angle of arrival just like we did for angle of departure. So that's 90 degrees. Let's just call it theta1. Okay, all right. And again, this is the angle contributed by this. Let's just call this theta2. And here is another one. Okay, this is the angle contributed by this. Okay, let's just call this theta2. Okay, everything is contributing certain angles, but notice carefully that this angle, this one, this theta, this is theta3. This theta3 is an angle contributed by the 0. Again, since zeros are in the numerator, if you calculate the angle of that, okay, that gets a plus sign, right? So we would have plus theta3, right? Plus theta3 minus theta1 minus theta2, and again plus angle of departure, angle of arrival, because angle of arrival is also the angle contributed by the 0 here. So any angle contributed by 0 gets a plus sign, and any angle contributed by a pole gets a minus sign, right? And that has to be an odd multiple of pi. So 2n plus 1 times 180 degree. Okay. So this theta3 is the angle contributed by a 0. This angle of arrival, which is theta a, that is also an angle contributed by this 0. So they are going to be positive. And theta1 and theta2 are angle contributed by poles. So they are going to be negatives. So with that calculation, what is theta3? I know that theta3 is approximately 90 degrees. So that's 90 degree. What is theta1? Theta1 is also 90 degrees. So of course we had a minus sign there. What is theta2? I can calculate theta2 by using the triangle here. What is the base of the triangle? 2 units. And what is the perpendicular of the triangle? 1 unit. So that's going to be tan inverse. So this angle is going to be tan inverse 1 by 2, perpendicular by base, and plus angle of arrival, right? And that has to be an odd multiple of 180 degrees. And again, we can pick and choose what kind of odd multiple of 180 degrees I want. So these two actually cancels out here. All right, these two cancels out. Let's again bring up the calculator and let's calculate the tan inverse thingy. Tan inverse of half. So tan inverse of half, that's 26.6 degrees. So minus 26.6 degrees plus theta a, and that's going to be an odd multiple of 180 degree. Okay, that's going to be an odd multiple of 180 degree. And again, I am, for my particular purpose, I am choosing it to be minus 180 degree. You could have chosen plus 180 degree, whatever, it won't matter. Okay, so that's theta a is minus 180 degree plus 26.6 degree, because I want my calculation to be within minus 180 plus 180, because writing something like 300 degree, it makes no sense. I could just write minus 60 degree, right? So 26.6 minus 180, right? So so minus 180 plus 26.6, that's minus 153.4, minus 153.4 degree. So minus 153.4 degree. Okay, so realistically speaking, this arrival would happen at minus 153.4 degree. So if I zoom in here, I will see that this is the 0 and this is approaching at minus 153.4 degree. So the approach of the root locus, if I zoom in, would happen this way, so that the angle, this angle is minus 153.4 degree, right? So that's the angle of arrival here, something like that. Okay, all right, no problem. So I can draw this rest of the root locus. All right, and again these are s equal to minus 1 plus j1, and this would happen when k tending to infinity, and this is s equal to minus 1 minus j1 happen at k tending to infinity. And let's just write a theta d, theta A, angle of arrival, equal to minus 153.4 degrees. Okay, writing one of them is just sufficient. So that's the complete root locus here. Okay. So again, the system remains underdamped. The system remains underdamped within these ranges. So I would say one within that range, greater than 0, less than 0.618. So I have real and unequal poles. So under real and unequal poles. So overdamped. Response is overdamped. Then at k equal to 0.618, we have critical damping. And when k is greater than 0.618, okay, it is, so we have complex conjugate pole pairs. So this is going to be underdamped. All right, so that's the load locus here. Any question? Again, as you grow your knowledge on these topics, you would see that by looking at a set of locations of poles and zeros, you would have some rough idea of how the root locus is going to look like, because that was the whole purpose of the technique. Okay, so you should have a visual understanding of how the roots would change their locations as I go on increasing the value of k in k. And let me just bring up the Ogata's book. Okay, and here in Ogata's book, you can see there are some typical examples of pole zero locations. So again, this becomes so simple after you have solved a few problems. If I give you certain random poles and zeros, open loop poles and zeros, if you know the open loop poles and zeros, you would have some idea of how the root locus is going to look like. Okay, so here are a few standard examples, right? Okay, the last example that you saw I did, okay, entirely came off the top of my head. Okay, because once you actually are familiar with these techniques, you would be able to draw a root locus without actually calculating anything. If I give you the locations of poles and zeros, you would have some rough idea of what's going to happen. All right, so that is something you will have to. Again, I believe this book is already with you. So in any case, just ask any question that you might have. Otherwise, we're going to end our discussion right now here. So thanks for being patiently going through. Thanks for patiently going through all the things that we have discussed today. So that would be the end of today's discussion. End of our discussion on the root locus technique. You would get quite a few exercise problems to solve. Okay, and I would suggest you solve those problems. And whenever you get stuck, try to figure out why you got stuck and try to use your computer, okay, especially the Python control module, to draw the root locus for you, to make it draw the root locus for you. Okay, and then try to figure out the things that you couldn't figure out earlier, right? Take the help of a computer and try to figure out. And then still, if you cannot figure out something, ask me. I will definitely help you. So with that said, this is the end of today's discussion. Feel free to drop any question on my email, and I will see you tomorrow. Thank you all.